Hey guys, this is going to be a review of water chemistry. So for most of you guys, this was your sophomore year. For some of you guys, it may have been sophomore and junior year. Some of you might still be taking it. If you do, ask me questions about it. But either way, let's see what we remember. So some of the content in this particular video are disturbing, so be sure you take everything with a grain of salt here. I apologize if I offend anyone. I'm not trying to do that. I just wanted you to remember some things. So, ooh, wow. So anyway, this is water. He's a really scrawny dude, but he can do really powerful things. And so water has a molecular mass of 18 atomic mass units. If you forgot how to do that, it's periodic table stuff. You take the atomic masses of the elements that make up the compound. So in this case, 2 hydrogens and 1 oxygen. You take their atomic masses and add them together. So 2 hydrogens, each hydrogen is 1. 1 times 2 is 2. And then oxygen is 16. Atomic mass of 16, so 16 plus 2 is 18, so an H2O molecule will have an atomic mass of 18 AMU, atomic mass units. But basically, water can do a bunch of really cool things, and there's a lot of compounds. For instance, carbon dioxide is a much heavier compound in terms of and it's also bigger, so you would expect it to maybe be able to do some of the same things that water can, but it's not even close. Water is a really small molecule, but can do lots of interesting things for being so small. First thing is that it actually will exist on Earth in all 3 phases. Not a lot of things do that. So talking about carbon dioxide, for example, we typically only see that as a gas, and the only time that we see it outside of its gas form here on Earth is either as a liquid in tanks, and then we really don't even see it, or as a solid in the form of dry ice, which we can see, but then it goes straight to a gas from that state, and we had to put a tremendous amount of energy and effort in to even create that. So, you know, water can be ice, liquid, or gas. Relatively easy to transition from those phases. So this next picture, do me a favor, go find your mom's favorite vase. Put that favorite vase in the fridge, but before you do that, and by fridge I mean freezer, but before you do that, I want you to cap it, right? Fill it with water, cap it. Then put it in the freezer for a few hours. Come back with your mom and say, "Mom, look what I did to your vase." And then watch her yell at you and scream at you, because that's what's going to happen. Because remember that water expands when it freezes. So if you have water confined in a space, it wants to expand and break out of that space, which is not what most things do. So let's keep rolling here. This game here is Red Rover. I don't know if you ever played that. It was banned in a few countries in the late 80s after some incidents that happened around the globe, perhaps at one of these schools that I went to, whereby, you know how the game goes, right? I mean, Red Rover, let Johnny come over, then Johnny comes screaming over and tries to break through, you know, the kid's arms right here. Well, if you hold on real tight, but Johnny's running real fast, then sometimes someone else might accidentally break a little kid's arm. I'm not saying it happened to me in my early years, but it might have, and it's really traumatic for people, so that's why they don't play it as much anymore. Anyway, when we're talking about Red Rover, we're talking about surface tension and capillarity, and that's one of the first things that we're going to talk about in this prediction thing that I've been telling you about. So we'll leave it at that. But basically, water molecules kind of play Red Rover. This dude looks nice and happy. Looks like he just got through eating, and what he's doing now is digesting his food. Most reptiles will lay on hot rocks to help them digest their food. Makes their blood flow a little bit quicker, because remember they're those cold-blooded creatures. so they can't regulate their body heat, so they use rocks to heat themselves up, which then helps their blood flow more, which helps them digest their food more. But the reason he sits on rocks is rocks heat up a lot faster than water. Water has a really high specific heat, so it doesn't heat up very fast. So it doesn't heat up very fast, and then it also doesn't cool down very fast. And then again, warning. Ooh, there's your soda versus Kool-Aid, and we all know that the majority of the contents, if you look at the ingredients in Kool-Aid and soda, is actually water. Most people would say, oh, it's sugar. No, if you actually look, the first ingredients is usually carbonated water or water, right? So water is the universal solvent. It dissolves a lot of things. We'll talk a little bit more about that. Then a couple other things. Got Bart Simpson here. Sulfuric acid is not a toy. Water, when it dissolves things, sometimes depending on what those substances are, it can change the pH of water. So water is a pH of 7, which means it's neutral. But when we add it to other things, it becomes the vehicle that creates an acid or a base, which we'll talk a little bit about the form of acid rain and things like that. Then this is Mr. Sparky. This is the electric chair, which basically electrocutes people on death row. This I put on here basically to tell you that water is not electrically conductive. Most people don't realize that, but covalent compounds do not conduct electricity. So if we have pure water, 100% pure, no additives, no preservatives, it will not carry an electric charge. So if we pass electricity through it, it won't go through it because it does not. It is not conductive to electricity. So water does not, I repeat, does not conduct electricity. So don't go around saying, well, Coach Joe said I can go jump in a bathtub with a toaster. That's not what I mean. Your bath water is not pure water. It has lots of things dissolved in it, things called electrolytes that then can create a potential difference in electrons, which then allows electrons to flow, which is electrical current, which then will electrocute. So don't do that. So let's talk about the most important property of water. It is what makes water so unique, and this is where we're going to camp out really for the next week or so at least. So let's make sure we unpack this. So the most important property of water is this: that water is a polar molecule. Okay, so you need to get that in your head right now. If I ask you, is water polar? Yes, it is polar. What makes water so unique? It's polar. Now, if I ask you what polarity is, we're going to have to do some work on that. So let's kind of unpack that first. So here we go. Basically, if you remember from chemistry, we have this thing called electronegativity or electron affinity. It's the ability of elements to attract electrons toward them. So some elements want electrons really bad, some don't really want electrons at all. So those that want it really bad have those high electronegativities, have those high electron affinities, and they really want electrons, right? And then there's some that don't. So let's look at it. Oxygen is one that wants electrons quite a bit. Hydrogen does not want them as bad. So if these two get together, you actually end up having a tug of war, right? And so oxygen's over here. It looks like everybody's hustling, right? And here's our electron on the rope, right? And oxygen is pulling pretty hard, right? Pretty excited about winning this tug of war battle. And then look at hydrogen over here. You got one guy trying, you got one guy, one hand on the rope and waving at somebody else, and then their third teammate's over here chilling in a chair, drinking a drink, right? So who's going to win this battle for the electron? It's going to be oxygen. But is hydrogen at least pulling some? Yes. So when you talked in chemistry about this becomes a sharing of electrons. And if you remember, there's covalent compounds and there's ionic compounds. In ionic compound, you're just going to get that electron ripped away from the other dude. In the covalent compounds, it's an unequal, or sometimes it can be equal, but it's a sharing of that electron. So in this case, because oxygen wants it more, hydrogen doesn't want it quite as more, still wants it, but doesn't want to give it up, but wants it a little bit. You know, it's still there. There's an interaction between the two. So oxygen is going to win this battle. The electron will be pulled closer to oxygen, but hydrogen is still there hanging on to that electron as well. And that's a covalent bond. And that is an unequally sharing covalent bond, which we give the term a polar bond. So that unequal sharing causes that polar bond. So in this particular case, what happens is oxygen is going to pull the electron toward it better than hydrogen does. Because it does that, that makes the oxygen slightly more negative, because electrons, remember, are negative. And then it makes the hydrogen slightly more positive. How do we know he's positive? Because he's sure he lost an electron, right? It's a larger, we'll talk about that later. Anyway, so as oxygen attracts those electrons towards it, it becomes negative feeling, and then hydrogen loses that attraction toward the electron, so the electron moves further away, which makes it feel more positive. So the way we denote that is this is actually turned sideways. This is a delta, lowercase delta, so it's a D with a minus around it. So when you see that, it would actually be flipped so that this would look like a D. So turn your head if you need to, so you can see that that's a D with a little minus, and that just means partial negative charge. Okay, so if that's a little crazy for you, let's just remember this. This to me makes it way more easy. Everybody likes polar bears, right? Look at that cute little guy. I mean, this guy, you just want to get up under his chin, give him a little scratch. Oh, so cute, right? Everybody sees them frolicking around with their Coca-Colas on the ice, right? Well, remember we were talking about. Oh my goodness! So remember that the water molecule is like a dead polar bear. I'm not so happy about polar bears anymore. Yeah, that was actually a polar bear that ate another polar bear and is carrying its head around. It did like a Mortal Kombat thing on it, right? And finish him. And so it's not quite like I'd like to buy the world of Coke, but anyway, it's a dead polar bear. So why is water a dead polar bear? Let's look at that. Let's get our polar bear out there, right? And then there's these things called lone electron pairs. When you did the Lewis dots in chemistry, you paired these up with their valence electrons. Don't worry about it. I'm not going to test you on that. But what happens is, remember the O is pulling the electron from the hydrogen closer to it, pulling the electron from the hydrogen closer to it. And then the hydrogens are kind of losing that electron a little bit, so they're becoming more positive. The oxygen is becoming more negative. So I call it a dead polar bear because in cartoons, how do we indicate a dead organism? We put X's for the eyes, right? So there's the X's for this guy. And then if I always ask this in class, everybody misses it. I say, so what kind of mouth does a dead guy get? And they all say, oh, it's a sad face. And then I make fun of them because no, you're dead. You can't have emotion, right? So it's actually just a line, right? So this is our dead polar bear. And now notice what that does. Because you have these X's that are over by the H, right? It shows us that the H's, tilt your head a little bit, are positives, right? And then down here away from the H's is negative. So now you have everything you need to know about your water molecule. So the positive charges are near the hydrogen, so this end is a partial positive, and then the other end is a partial negative. So remember this. You will be tested on this, quizzed on this. You need to understand what the water molecule looks like. So if we went back to this picture here, it would probably be flipped upside down, but you would have, what you would have is this would be the O, and then X for an I, X plus for an I, and then the minus would be here. So notice you have the positive side of the atom, or of the molecule, and then you have the negative side of the molecule here. So that is polarity. That is the general properties of water. So you'll probably have a quiz over this. So if this was an ed puzzle, be sure that you looked at those questions that you just did, because they will probably be similar questions to a quiz over this. Next video up should be prediction time. So make some predictions, and then next week we're going to unpack how amazing this water dude is.